Welcome to another presentation about heat pumps. Maybe like that. Heat to cool is a bit of a motto. My name is Lergenmüller, and I'm a product manager and responsible for heat pump equipment from the GEA, from the GEA company, which is doing both cooling and heating for many, many years and many decades. Why we need heat pumps, I'm sure it's been pretty clear, but here's a statistic that I don't want to go through in every detail, but the key message, what this statistic says, and that's the energy demand, the thermal energy demand, only in the European Union, but the picture is pretty much valid for on a global base. And the key message is that the heating energy is still mostly realized with fossil fuels. First of all, we have a lot more heating demand than cooling demand. Second, through this statistics in the European Union, actually that's a few years old, but I think the picture hasn't changed dramatically. So still well over 90% of the heat is generated by burning fossil fuels. We're burning coal, we're burning gas, we're burning oil. And the refrigeration energy is just a fraction of it. That's mostly electrified. So what we need to do now, of course, is also to make all the heat supply more sustainable. And heat pumps are one of the ways to do that, up to a certain temperature level, obviously. And heat pumps are running, or compression heat pumps are running on electricity. So you might argue, well, what if the electricity is coming from coal plants? If that's not clean electricity. More sustainable you are with heat pumps anyway, even if your electricity is entirely generated by fossil fuels. And the reason is the efficiency. Here you have a classic boiler, a fossil heating device, at an efficiency of 80%. So that means if you have one energy unit of primary energy, you get 0.8 units of usable heat. A heat pump, you take heat source, basically, you have available heat source. The heat source is charging the evaporator of the heat pump, the refrigerant evaporates, and then it's compressed and pushed to the desired temperature level, where the heat pump releases heat to any kind of consumer that you want. Our heat pumps are able to transfer heat to a water or to a glycol circuit, and the applications are endless. Anywhere where heat is needed, based on a glycol or a heat carrier circuit, can be provided with our heat pumps. After the condensing, it's expanded back to the lower temperature and pressure level. So you see a cycle that is exactly like a refrigeration, like a chiller cycle. I said they are powered by electricity, by an electric motor. And in the worst case, you need 2 units of fossil energy to create 1 unit of electric energy. However, that 1 unit of electric energy can provide up to 5 or even more units of heating capacity. And the reason is because you have the heat source balanced. So you have available heat source. The heat source is for free. You don't need heat source as a specific temperature level. So heat doesn't mean it's hot. You can have cold heat. You can have heat from the environment, from rivers, from lake, wastewater, breakage, sewage water, whatever you like. And the temperature doesn't matter. You push it up to the desired temperature level. So this is the reason why if you have the same heat output, if you want to have the same heat output with a classic boiler, you need a lot of more primary energy. So the factor, in the worst case, is still 3:1, meaning that a heat pump, a sustainable heat pump, like a GEA heat pump, of course, only needs 1/3 of the primary energy that a classic boiler needs. When we talk about sustainability, and when we talk about heat pumps, we have to talk about refrigerants as well. And if you really want to go net zero, zero emissions, you would ideally take fully natural refrigerants, for example, like ammonia. We are a bit biased because we have been dealing with ammonia for hundreds of years, but we are convinced that in a respective application temperature area, ammonia really is the best refrigerant that you can go with. The benefits of ammonia And here I'm showing you a calculation example. I'm calculating a screw compressor at a certain size, at a liquid heat source, at slight ambient temperature level or typical industrial waste, chiller waste heat levels. And I'm calculating this for heat carrier supply of return supply 70 to 90 degrees Celsius. These are typical criteria conditions for heat pump applications, whether it's in the process heat, for not the highest temperatures, or also for heating grids. For facility heating, you rarely need temperatures above 90, 95, or 100 degrees Celsius. And then if we look at a specific refrigerants, and we look at a few common values, like the efficiency, the heating rating, and then of course the volumetric heating efficiency, a constant factor for each of the refrigerant, and the global warming potential, meaning the CO2 equivalent that a refrigerant releases once it's kind of spoiled into the environment. And there's now a lot of data that, again, I don't need to go through every of the numbers. On the top row, you have some values for the ammonia. And then there are values for other refrigerants, sometimes commonly used or in discussion for heat pump applications, and the upcoming R1234, whatever, YF, ZE, just to compare with each other. And we see that the ammonia, based on our equipment, is a lot more efficient. In this case, it's 40% more efficient. Secondly, you're getting twice the capacity with one unit with ammonia than you would be getting with a different refrigerant. And third, this is based on that list, if you're really very strict, the only refrigerant that actually has a zero global warming potential and also a zero ozone depletion potential. So once we have ammonia, it's really fully climate neutral. We know that ammonia has some criteria, has some characteristics in large concentrations. You have to take care of this. There's a toxic and flammable elements in ammonia. But you also have that with a lot of different refrigerants. So from a safety point of view, ammonia is still, it's not rocket science. Your safety, machine room safety, it's not a lot of more effort than with any other common refrigerants. By all the praise about ammonia, we are talking about a specific application area. And that depends on the design pressure of our equipment, which typically goes to 63 bar. So yes, with ammonia, we are also limited in temperatures, below 100 degrees Celsius. So it's fair to say that in a respective application area, temperatures and capacities, ammonia has these advantages. When we talk about higher temperatures, we also have to talk about different refrigerants, and then other refrigerants have their rightful place in the portfolio. Our application range, I was already mentioning that we are limited with the temperatures. And to give you an idea of our standard ammonia heat pumps, what they can do in terms of temperatures and capacities, then there is a graph which best visualizes the whole range. So when we talk about the heat sink temperatures, really the supply temperatures that your hot consumers need, we are starting at 45, 50 degrees Celsius. Any temperatures below can be covered with more common chillers. If you use the waste heat of the chiller at temperatures up to 50 degrees Celsius, and then the heat pumps start. So we have reciprocating heat pumps based on different reciprocating compressor series. In this case, there are 3 different compressor series. Altogether, this is 11 models, and we are spanning a capacity from a few hundred kilowatts to about 2.5 megawatts. The capacities are staying pretty much constant, irrespective of your heat sink temperature level. If you change your heat source temperature, however, the capacity shifts. Lower heat source temperatures on the cold side means less capacity is available with one compressor, so that whole chart would shift a little bit to the left. And if you increase your heat source temperature, which is a very smart thing to do, if you can do it, the whole system becomes more efficient, and the whole chart would move to the right-hand side. So with a specific compressor model, you gain more capacity. Our standard screw compressor heat pumps are operating between 80-85 degrees Celsius on the top temperature, up to slightly larger capacities than on our reciprocating compressors. And if we're really talking about, if we're really going to go for the large capacities, then The standards are becoming less available, also for different components. Like you just don't find standard motors that generate 1-2 megawatt of driving capacity. So this is more customized area, and then we can go up to 10 megawatts with one unit. So if you have super large heating grids for 40, 60 megawatts, which happens, we get those inquiries, then you would typically go for a very large unit, and you would still need maybe 3-4 units. Our portfolio, you've already seen piston heat pumps, screw heat pumps. We have compressor units, compressors and units. There are reciprocating compressors and packages. For the reciprocating types, there are 11 types between a design pressure of 39 to 63 bar. Here you see the swept volume at 1500 rounds per minute. That's the top speed for our recips. And then there are screw compressor counterparts. There are more types, and there's a larger capacity range available. And we also now have models up to 63 bar, meaning, again, the maximum target temperature is 95 degrees Celsius. Complete standard heat pumps based on the compressors and the packages. There is the so-called Lergenmüller. That's our standard reciprocating heat pump based on all the available reciprocating compressor models. And then there's the screw sister or brother, a standard screw heat pump based on 7 of the screw compressor types. And here you also see the swept volume range. The reason why we are not adding the larger compressors to the standard heat pump is simply what I mentioned before. At some point, it's hard to find standard components, so it's more customized job. Then there is a new product as well. It's called the GEA Blue-Red Fusion, and it's based on a standard chiller and heat pump combination with all our Lergenmüller models or Red Astro models. And on the low stage side, there are our blue chiller models. They have similar philosophy as the red heat pumps, only at lower pressures for chiller applications. So we combine these two models into one product, and we have a combined chiller heat pump device, or it's kind of a two-stage heat pump if your heat source is coming from a very, very low temperature. The bespoke and customized heat pumps are available basically on all applicable compressors. They cover the widest temperature and capacity ranges, and we can create multi-stage systems as well. Serial heat pumps that share, or that the whole capacity is distributed on several modules, and some can run on a little bit lower temperatures, the other one can run on a little bit higher temperatures, so you can create a very, very efficient system for large capacities. Let's take a closer look at the Lergenmüller. So you have a picture of how this actually looks like and how this is dimensioned depending on the capacity, small to large, a few hundred kilowatts to 2.5 megawatts. Then you can imagine this is the length range and the width range, the height approximately, weight, ammonia charge. That's also a benefit when we talk about ammonia, and people still feel a little bit inhibited. The charges are very low. Yeah, you see you need 35 to maximum 95 kilogram ammonia on this kind of heat pump. Sound pressure level, it's very much depending on the type of speed, the type of compressor, so there is a bit of a big range, but this is it. Then some highlights, actually. Here in the middle is our reciprocating compressor, and we're really proud of the latest developments based on the long-term experience with our V-series design for the refrigeration compressor. Even in these low-pressure compressors, but also in the high-pressure compressors, we are having a unique housing design and creating a very good temperature separation between the suction and the discharge side. And this means that we are the only one over the entire range that does not need an extra cylinder head cooling. Then there are special and new bearing materials, and that leads to really the highest efficiency. It's been tested so many times in the field, in our factories, so we can safely say this is very, very, very sustainable compressor, both in an ecologic, but also then, of course, in an economic sense. Safety, reliability, there's a patented ammonia drain system, because that's one of the most important things to keep ammonia drain out of the compressor, keep the liquids out of the compressor. We have a lot of special devices like that one to foster our reliability and longevity. Coming away from the compressor, the heat exchanger set on the right-hand side here, it's based on a patented compact evaporator-separator combination on the low stage. And then on the hot side, the heat exchanger that actually transfer the heat to your consumers, to your heat carrier. It's based on a very flexible and individual heat exchanger set with an optional subcooler and desuperheater. So we make sure that based on the very specific conditions that you have, we find the perfect heat exchanger that give you the best efficiency and the capacity and the temperatures that you need. And finally, controlled by our Omni control panel. It's a very unique controller because it's not just a PLC, it's really an industrial PC with a lot of different functions and that also fosters reliability and efficiency. There are energy management systems, you have smart sequence control and so on. There are multiple functions. It's kind of a word in itself. I could talk a whole day about this control panel, but you can see that also on our booth, of course, and experience everything. A totally different example is when you talk about large custom heat pumps. So here you see like our regime on the side, and this is a big unit, a 10 megawatt unit that we built last year for a district heating project in Scandinavia using one of our largest screw compressors. You can already see the big motor here on the computer model that's really complete out of standard. Here a few stats for this project. You see the weight and the charges, that's really a lot more than our standard heat pumps. Yeah. Finally, last slide, the calculation examples, factories going neutral, going carbon neutral. We have food factories that are following a so-called cook, can, chill process. What happens is they're cooking at low pressure, cooking, low temperature cooking, they're cooking their food, they're chilling the food afterwards, and they have cleaning water, they have an air conditioning, so they have different energy demands, different temperature demands. And typically, in the old way, they are putting in a boiler. It's quite easy, of course. It's very simple. And then they worry, we need a refrigeration device. Let's have a chiller. Again, chiller is creating waste heat. It's not used. And in this specific case, this was the energy consumption here. The capacities needed and the annual consumption based on the operating hours. And what we simply did is to replace the boiler, but also the chiller, by a heat pump unit, a GEA Red Astrum, that can do both, that can do cooling on the low side and providing the heat on the hot side. So the customer specifically wanted that streamlined unit because he also wanted to prevent or to throw out the old chiller. So he has that system now, saving a lot of space and also saving a lot of energy. This chiller heat pump, so to say, consumes more energy than the chiller, but he could completely get rid of the boiler. So his savings are massive. Every year he's saving these amounts of energy and money. So the payback time of these devices are just barely 2 years, approximately. Thank you very much. So in the end, heat pumps, they're an integral element in decarbonizing our industries and of course also communities. You've seen an example from the process heat in the food industry, but also networks, local heating grids, facility heating. That is of course also be met with heat pumps. And we have a lot of inquiries, a lot of projects. Let's get started, and thank you for your attention.